In order to provide the redundancy of default gateways to hosts connected to our networks, we often resort to using first-hop redundancy protocols. First-hop redundancy protocols are Cisco's Hot Standby Router Protocol, the standardized Virtual Router Redundancy Protocol, the VRRP, and Cisco's Gateway Load Balancing Protocol. In this module, we are going to discuss these three protocols in some detail, but before that, let's take a look at what is the actual need for these so-called first-hop redundancy protocols. Luckily, explaining that is not going to be too much of a problem because that's a relatively simple thing to explain. Now, in most of our networks, in most of enterprise networks, what we have is some sort of a design where we have some gateways to the outside world. Let's call them routers 1 and routers 2, and behind these gateways we have some sort of a network where we have our end hosts that are connected. Now, these things can be a little bit more complicated. Of course, we can have the firewalls, we can have multiple VLANs, we can have any number of things that exist in our network behind these gateways or make this internal design a little bit more complex, as we are going to see in some of the other videos. But this is the most simplistic approach to explaining the need for first-hop redundancy. And now let's say that these gateways here are connected to the outside world, that they're connected to the internet, for example. Now, on this segment here, we may have multiple hosts that are connected to our network. Now, these hosts here, they need to be able to access the services that internet provides. They need to be able to browse the websites, to watch YouTube videos, whatever else, and among other things, watch these videos here. But which one of these gateways, these redundant gateways outside of our network, should these hosts use? Well, this is where the first-hop redundancy protocols come into play. In most cases, we are not going to have a routing protocol running on this segment. Now, in some cases, you might even have that, but in vast majority of situations, we don't have that. So what we really need to be able to do here is to be able to provide the redundancy between our routers 1 and 2, which could be multi-layer switches. So these routers here, they could be multi-layer switches to which these hosts are actually connected to, but here I'm looking at the actual logical interpretation of things. So we are looking here at the layer 3 redundancy, not necessarily layer 2 redundancy. So how can we provide these redundant gateways? Well, there are multiple solutions for this problem. One of the simplest approaches is to say that, let's say, half of our network here is going to be using R1 as the gateway, and the other half is going to be using R2 as the gateway. As you might think, what's going to happen if R1 fails with these hosts here? Well, obviously, they are going to lose the connectivity to the rest of the network, to the outside world, to be more precise. Now, and also, how are we going to maintain this? Are we going to have different information sent in our DHCP responses? Entirely doable thing. But wouldn't it be much nicer if these hosts, if all of these hosts here could use the same information that the gateway is, let's say, shared between R1 and R2, that there is some sort of a virtual gateway that exists, and these hosts point to this virtual gateway, and then either R1 or R2, or maybe both of them, are actually going to be in use and send our information outside without our end hosts here actually participating in any sort of dynamic routing. That is exactly what first-hop redundancy protocols solve. They are going to allow us to use a virtual gateway on our physical devices and send the traffic out of our network. As we will see, some of them offer some sort of load sharing services, and some of them don't really offer. Still doable thing, but not very, very straightforward. So let's dive into and see how HSRP, VRRP, and GLBP actually work. The first protocol that we are going to look at is going to be Hot Standby Router Protocol, or HSRP. Now, when we talk about HSRP, it's important to understand that this is an active standby relationship. When we have active standby relationship, that simply means that there is going to be one device forwarding the traffic out of our network, and the other device or devices are going to be in a standby condition. Now, when I say in a standby condition, I should clarify here that the standby state in HSRP is something that only one other device could be in. So imagine that we had, say, 3 routers that are providing redundant gateways for our network. One of them would be active, the one that is actually forwarding the traffic out. The next one would be standby, and the third one would, technically speaking, be in something that HSRP calls the listen state. Now, the listen state simply means that that router is observing the hello messages that are exchanged on this particular network segment, but it's not next in line of succession should the active router fail. Now, if the active router fails, the standby router may take or will take over from the active router, and then the router that was in a listen state is going to take over. Now, this taking over and failing and so on is something that is part of HSRP election process. Now, the election process is conducted using the exchange of hello messages, which are sent on the local segment in the VLAN, and they are sent to the multicast destination, the link local multicast destination that we can see here, which is 224002, which means all routers. These messages are UDP messages, and they are sent on the port number 1985. By default, they are sent every 3 seconds with the timeout, the hold down timer, call it whatever, of 10 seconds, or more easily remembered as roughly 3 times the hello timer. These timers obviously can be modified. You can specify pretty much any range in number of seconds, but you can also specify this in number of milliseconds. So we can specify the timers, the hello timer, let's say in any range between 15 and 999 milliseconds. Is this a wise thing? Well, if the routers detect 3 missing hello messages or detect missing hello messages within the specified timeout period, the routers are going to declare that particular peer as dead or missing or non-functioning, and they're going to promote themselves up. However, keep in mind that sending messages every, say, 15 milliseconds, while it can speed up the recovery or detection of the failed peer, can also introduce additional traffic on that particular network segment and can also cause additional CPU loads on the routers processing these messages, which could in turn make them forgetful about sending their own hellos, which could in turn lead to detecting the neighbor that's not exactly dead, but is just busy processing the hello messages. So you might need to find a fine balance of how often you want to send these messages versus how fast you want to detect the failures in your network. In any case, when we have these hello messages exchanged, which router is going to become the active router? It is going to be the one that claims the highest priority. The default priority value is 100, but you can specify other values if you want a deterministic behavior in your network. If 2 devices are claiming the same priority and they happen to be the only devices on that network, they simply are going to fall back to the IP address, the configured IP address on an interface in that network segment, and the one with the highest IP address is going to win. Now, what is going to happen if a particular device wants to take over? Say our 3rd device shows up on the network and it has higher configured value. Well, this is something that we call the preemption. When we have preemption enabled, and for HSRP the preemption is disabled by default, if we enable preemption, the device claiming higher priority is going to become active, and then there is going to be not a promotion of roles, but it's going to be sort of a demotion of roles. The device that used to be active will fall back to being standby, and the one that was standby will fall back being in a listen state. This is all good, but what happens if this is not desirable behavior? Well, in that case, you can resort to, say, disabling preemption, or if you're afraid of rogue HSRP speakers, you can actually use authentication. Authentication in HSRP can be configured in 2 modes. We can use plain text or MD5 authentication. Sometimes it's actually desirable for the router to willingly forfeit its status as the active router. This is in situation when, for example, we have an internet gateway that has just lost the connection to the internet. In that case, we really don't want to be the active router on the segment. We can do that with HSRP using a so-called tracking process. Now, with the tracking process, what we can do is we can track the particular state of an interface. For example, if the interface is up, we are going to say that, okay, the tracking state is up. Or we can track a particular object. Now, in iOS, a tracking object can be any number of things. It could be, for example, an IPSLA probe that pings our default gateway, say the internet gateway, on the ISP side, and if we don't receive ping responses from the other side, we declare the tracking object to be down, and then the HSRP can use this information to lower its priority. Combined with the enabled preemption, this could allow the router to actively tell some other device that, hey, look, I don't want to be active on this segment anymore. Can you please take over? This is how HSRP is most often used, because we really don't want to have HSRP provide services, or the active router provide services when it's not connected to the rest of the world. HSRP uses several different addressing methods to communicate. The first thing that we need to configure when we are configuring HSRP is the virtual IP address that our hosts on the subnet are going to be using as the default gateway. This is an administratively configured IP address, and it needs to be from the same subnet as the physical address of an interface that we are configuring. If you try to configure something that is outside the physical subnet that is already configured, iOS will give you a warning message. But more importantly, what we need also is a virtual MAC address. And here you don't really have that much choice. Even though you can tell the router to actually use a physical MAC address of an interface, by default what the routers or switches are going to do, they're going to be using a virtual MAC address, which is from the range of 0C07ACXX, where XX is simply a group number. So if you are using HSRP group standby group 1, XX will be 01. If you are using 5, it will be 05, and so on. But keep in mind that this is in hexadecimal format, not in decimal format. So for example, group 16 won't be 16, it would be 10, because we do have those digits that are represented by letters, A, B, C, D, E, F. Also, load balancing using HSRP. This is very important. Technically speaking, HSRP does not do load balancing, but we can still do load balancing with HSRP if we think back about the things that I said in an introduction to this video. What is the need for the load balancing? What we could do is we could have on the same interface, on the same segment, on the same set of routers, on the same pair of our redundant gateways, we could have multiple HSRP groups configured. And we could have one virtual IP on one group and one virtual IP on another group. And then we could have, say, our DHCP lease out the default gateways that are either one or the other. But now you're thinking, what would be the need of this? Why do I need a virtual protocol? Why do I need a hot standby routing protocol when I'm going to fall back to using different gateways? Well, think about it. If we were using physical IP addresses on our gateways, the situation that we are going to end up with is that if one of these gateways is physically unavailable, those routers that were, those hosts on the segment that were configured with that particular router as the gateway, they will not be able to access anything outside of the network. But if we use the virtual IP address that could be on one or the other physical gateway, what's going to happen when one of our physical gateways fail? We are obviously going to lose the load balancing capability in our network, but we are not going to lose the connectivity with the rest of our network, because the virtual IP address that hosts are using as a gateway is no longer serviced by the failed router, it is used by the router that is still operational. So there are even some benefits in doing this. Another way that the load balancing could be sort of simulated in HSRP environment is to have different HSRP setups for different VLANs. Let's say that we had 2 VLANs in our network. We could have 2 gateways in our network configured in such a way that gateway 1 is the primary gateway, is the active gateway for VLAN, say 10, and a standby for VLAN 20. And in VLAN 20 we could have gateway 2 be the active and gateway 1 be the standby. That way the traffic from VLAN 10 by default is going to be going through gateway 1, and traffic from VLAN 20 will be going through gateway 2 until one of them fails. In that case, all the traffic will be going through the one that hasn't failed yet. Let's now take a look at the configuration example of HSRP. Now, in this case here behind me, what I have is actually a configuration that is a little bit involved. Here I have 2 configured HSRP groups. I have standby group number 1 and I have standby group number 2. There's no particular reason why I did it that way, but what I really wanted to emphasize here is the possibility that we want to do, say, load balancing as I just described. So let's take a look at these 2 configuration examples separately. So I'm first going to go through the configuration of standby group number 1. The first line here, standby 1 IP 192.168.10.254, is basically configuring a virtual IP address that we are going to be using. Standby 1 priority 150, the second line of the configuration here, configures the priority of this interface in this segment to be 150. So we are going to have this a little bit more than the default value of 100. And the third configuration line here is going to enable the preemption. So we want to be able to take over from another device if another device is primary, but we also want to be able to forfeit this in a case that we want to have some other device take over from us. The fourth configuration line here, standby 1 authentication MD5 keystring 0 Cisco, is actually configuring the MD5 authentication. So for group 1, we are going to be using authentication, and that will be MD5 authentication. Now, this line here, line number 5, is an interesting line. In this line here, what we are telling our device is to track the status of interface fastEthernet 01, and in a case that that interface goes down, decrement the value of our priority by 100. In other words, make this here be just 50 should interface fastEthernet 01 fail. Now, the standby configuration 2, and here again I'm going to look at line by line. So here at line number 1, again we are configuring a virtual IP address, and we can see here that this is an IP address that is in the same subnet as the previous one. It's simply a different IP address. I'm configuring in line number 2, I'm configuring priority of 100. This is the default priority. This is not something that I would have to configure or that would necessarily show up in the configuration, but nevertheless I put it here just to kind of show my intent. So my intent here is that this device is going to be active in group number 1, and it's actually going to be standby in group number 2. So some other device that might be on the same VLAN is actually going to be having the exact reverse of the configuration. Again, in line number 3, I'm enabling preemption. In line number 4, I'm configuring authentication. This time, this is not MD5 authentication, and this is going to be simply plain text configuration, plain text authentication. And finally, in line number 5, I'm configuring tracking of object 25, whatever that might be. So this is defined elsewhere. Here I'm just referencing that other object that is going to be monitored by a object tracking subsystem in iOS, and I'm saying that should this object go down, decrement the value of our priority by 100. As you can see, the configuration of HSRP is relatively straightforward. Let's now see how all this actually works. To do that, I'm going to set up a very simple network. I'm just going to use two routers, and let's call them my R1 and R4, and they're going to be connected to the same VLAN. Now, these are obviously going to be connected through some switches, but I am not going to be focusing now on that particular switch configuration. It's simply access ports in the same VLAN. And this here is going to be my Fast Ethernet 00 interface, and this here is going to be my Fast Ethernet 00, and these two routers are going to be in VLAN 10, so I'm going to give them an IP addresses from 192.168.10/24 range. On this side, I'm going to be using 1, and on this side here, I'm going to be using .4. So what I want to do now is I want to configure HSRP between these two routers here with, let's say, R1 here being the active and R4 being the standby router. And I want to use .254 as my virtual IP address. Furthermore, what I would like to do is I'm going to have Fast Ethernet 01 interfaces here connected to these two routers, and I'm going to be using them to show you how the tracking of the status of the interface or of the gateway on the other side might actually work. So let's go ahead and configure this. So the first thing I'm going to do is I'm going to make sure that I do have some communication between R1 and R2. I'm simply going to say show IP route connected here, and I can see that I have the connected route. I'm just going to make sure that there is a connection between R1 and R4, and I do have that connection. So I'm going to go ahead and configure my Fast Ethernet 00 interface here for HSRP. So I'm going to be using group number 1. So I'm going to say standby 1 IP 192.168, and I'm going to deliberately make a mistake here. So I'm going to say that I want my standby IP address to be 192.168.1.254. And as I have expected to see here, I'm going to get a warning that this address is not within a subnet on this interface. So when I'm configuring HSRP, my standby IP address needs to be from the subnet that I'm already using on the interface. And by virtue of configuring this IP address, my HSRP is actually already up and running. And I can see that if I do show standby. So with the show standby command, I'm going to see now that my HSRP has activated. The router is not yet in active state. We can see that when I ran this command, it was actually in the speak state. By the time I have actually completed saying this, what I can be seeing here is that it actually changed state to active. It went from standby to active. So just configuring the IP address, the virtual IP address for the standby command is enough to activate your HSRP. But now let's configure that other stuff that I mentioned. I want to make sure that my R1 is going to be active and R4 is going to be standby. To do that, the easiest thing to do is to actually change the priority. So I can say standby 1 priority, let's say 150. So if I do show standby now, actually I have that in my command history, I will see here that it says that the priority is 150 and it is configured as 150. So this is the actual priority that is right now in use. This is going to come as very, very important because when we have the track object, I might have the difference between what is an actual priority, the operational priority, and what is the configured priority. So let's go to R4. On R4, I'm going to pretty much repeat the process. I'm going to go to Fast Ethernet 00. I'm going to say standby 1 IP 192.168.10.254, which is going to enable HSRP there. So if I do show standby, I will see that now my state is listen, and I'm going to be in that state because I'm going to be listening to the incoming hellos from the other side. Now I'm speak, I'm sending the hellos to the other side, and very, very quickly what is going to happen is that this device is going to switch from the speak to standby state. And this is exactly what I wanted. It is going to be in a standby state because R1 is in active state right now. But now let's see what happens when some things go, say, wrong in my network. what I would like to do here is I would like to configure, say, R4 to lower its priority by, say, 50 in a case that fast Ethernet 01 on this router goes down. So the first thing that I'm going to do is I'm going to make sure that my fast Ethernet 01 interface is up, so that while I'm tracking it, I can see that priority is actually correct. So I can see that my interface didn't change state here to up, which probably indicates that I have already done no shutdown on it, and that is true. So I'm going to go to fast Ethernet 00, and I'm going to say standby 1 track, and here I have several options. What I'm going to do is I'm simply going to tell it to track the fast Ethernet 01 interface, and we want to decrement the value of priority by 50 should that interface go down. So if I do show standby, now this is what I am seeing now. I can see that priority is 100, that the default priority is 100, and I can see that I am tracking interface fast Ethernet 01, that the state of this interface is up, and that it will be decremented, but priority will be decremented by 50 should this interface go down. Let's give this a go. So I'm going to go to fast Ethernet 01, I'm going to shut this interface down, and let's see where our show standby stands now. So I'm running show standby, and I can see now that my priority is 50 because the state of the tracked interface is down. Now, this didn't change anything in our network because router 1 was the active router and router 4 was the standby one. Let's now go to R1 and let's say track an object instead of tracking the status of an interface. First of all, when we are configuring the tracked object, we have to figure out what exactly are we going to be tracking. So in this case, I'm going to be tracking the interface fast Ethernet 01, but I'm not going to be tracking state of the interface up or down. What I want to do is I want to track, say, the IP routing capability of that interface. Is this interface capable of helping us route the traffic? Now, how can interface help us route the traffic? Well, if it has an IP address configured on it. So if I do show run interface fast Ethernet 01, for example, I can see now on my R1 that this IP address is configured. I can see that it has IP address 10.10.10.1/24 configured. So the first thing that I'm going to do is I'm going to configure a tracking object, track, and then I specify the number of the object that I want to track. And here I have many different options that I can use, but what I want to do is I want to do interface and then fast Ethernet 01 IP routing. So this is what I want to be tracking. I want to be tracking the capability, the IP routing capability of this interface. Here in this sub-configuration mode, I can specify, for example, the delay when the, say, interface loses its status, that I am going to wait a little bit before the tracking object goes down, or I can wait for the carrier delay timer expires, or any sort of advanced waiting situation that I need to have. But I really don't need any of that stuff. So I just want to define a very, very simple tracking object. So if I do now show track 1, what I'm going to be seeing is that interface fast Ethernet 01 IP routing capability is tracked, and I can see that IP routing is up. So the router thinks that this interface is okay with the routing capability. Now let's use this object number 1 in our HSRP configuration. So I'm going to go to interface fast Ethernet 00, and I'm going to say standby 1, I'm going to say track, and instead of specifying the interface, what I want to specify now is the tracked object number. So I want to track this tracking object number 1, and what I want to do now is I want to decrement my priority by, let's say, 180, because my priority is, well, what is my priority right now? I forgot. So let's see, show standby is 150. So let's say track, standby 1, track 1, decrement. So I want to decrement it by, let's say, 140. I could even say 150, but I want to leave some non-zero value there, no particular reason. So I'm going to decrement this value by 140 should my tracking object go down. So this is what I have configured now. If I repeat my show standby, I can see now that priority, the current priority is 150, the configured priority is 150, and the time tracking object number 1, that the status is up and then it will be going down, the priority will be going down by 140 should my tracking object go down. Let's bring our tracking object down. The easiest way to do that is to go to fastnet01 and say no IP address. So I'm just going to remove the IP address from an interface. Now, take a look at this. Now I can see that interface fastnet01 IP routing state has changed from up to down. So if I do show track, here I'm going to see that IP routing state of this track object is actually down. If I do show standby, I'm going to see now that the tracking object state is down, that priority is 10, even though we had it configured as 150. However, this did not result in router 4 taking over. I can still see that the state here is active. The reason for that is that by default, preemption is disabled in HSRP. If I wanted my R4 to take over in this situation, I would have to enable preemption. But where? On R1 or R4? As it turns out, I need to do that on R4. On R4, where we can also see that the preemption is disabled, what we need to do is we need to tell it it's okay to take over should the active router have lower priority than you. But is this an actual case right now? Well, let's take a look. What we can see here in the output of show standby is that active router is 192.168.10.1, which is our R1, with a priority 10, but our priority is 50. So this router should be taking over if we enable preemption. Let's do that. So interface fastnet00, what I'm going to do here is I'm going to say standby 1 preempt. Now that I have enabled the preemption, what is going to happen when the hello messages get exchanged is that my state is going to change from standby, actually from standby to active, and on R1 I'm going to see the state changing from speak or from active state to standby. When it comes to VRRP, or the Virtual Router Redundancy Protocol, there are some really good news if you know and understand how HSRP works. Because VRRP and HSRP are virtually identical. And for that reason, I'm going to talk very shortly about VRRP. I'm just going to highlight the differences between the two, because if you really understand how to configure and what show commands to run for HSRP, you pretty much know what to expect with VRRP. So the first major difference between HSRP and VRRP, other than the fact that HSRP is Cisco proprietary and VRRP is standardized, is that active standby is no longer called active standby, it's called master and the backup relationship. The master router in the VRRP configuration is the one that is doing the forwarding. All other devices are simply called backup devices. The election process is again done using hello messages that are this time not UDP. They are sent to a dedicated multicast address, a link local multicast address of 224.0018, but not UDP, and this time it is a specialized IP protocol 112 reserved for VRRP. Again, the election process first takes into account the priority, the higher priority wins, and then the IP address, given that the priority between two devices is the same. Unlike HSRP, in Cisco implementation of VRRP, preemption is enabled by default. That means that you don't have to enable it in a case that you want to have a router with the higher priority take over from the router with the lower priority, which is very useful when you are using tracked objects, as we described earlier. Virtual MAC address is again slightly different in a case of VRRP, and it is going to be 4 zeros followed by 5 E0001XX, where XX is simply going to be the group number. Again, remember, this is in hex. When it comes to the configuration and indeed the show commands, whatever you used for HSRP, just replace the standby there with the VRRP and you are good. So instead of configuring standby 1 IP and then the IP address, you are simply going to say VRRP 1 IP address and so on. Instead of doing show standby, you are going to be doing show VRRP commands. Really, this is it when it comes to VRRP. While HSRP and VRRP were virtually identical, Gateway Load Balancing Protocol, or GLBP, is rather a different beast. How is it different? Well, first things first, it is Cisco proprietary, so it is not standardized. VRRP is standardized, and HSRP to some extent is supported by other vendors than Cisco. GLBP, on the other hand, is true Cisco protocol. It offers true load sharing. Now, what do I mean by true load sharing? In the case of HSRP and VRRP, we could create multiple groups per interface, and we could have clients use different IP addresses to access the services provided by our gateways, but that's not real load balancing, because if we don't have this additional configuration in place that different clients use different gateway address, we cannot provide any load balancing services. And besides that, we are relying on something outside the configuration of the first redundancy protocol to help us with load sharing, like for example the DHCP services. With GLBP, what we actually do have is multiple routers on the segment being able to forward the traffic. This is accomplished by separating the roles of something that Cisco calls the AVG, or the Active Virtual Gateway, and the actual forwarding device, which is called the Active Virtual Forwarder. Now, the role of Active Virtual Gateway is to respond to clients' ARP requests. It is going to respond not with its own not with its own MAC address or its own configured virtual MAC address, but it's actually going to respond with the actual Active Virtual Forwarder's MAC address. I'm going to explain this in a little bit more detail. For now, I'm just going to give you a quick overview of how the protocol works. Now, when the client receives a MAC address for the forwarder, it is going to be using that address there. Now, imagine that we had multiple forwarders on the segment, and that for every subsequent ARP request, the Active Virtual Gateway responds with a different MAC address. There we go. Different clients will be using different gateways with the same IP address of the gateway, but they are going to think that they have different MAC addresses. Now, these Active Virtual Forwarders are also elected, but they are not elected based on the priority. They are elected based on weight. And here, think about the tracking objects. Each Active Virtual Forwarder is going to be claiming a certain weight that it can associated with certain interfaces, say, being up. If no tracking is implemented, all Active Virtual Forwarders are going to be claiming the same weight, and then certain number of them are going to be used for forwarding. There is currently a limit of 4 Active Virtual Forwarders per segment. Now, this is a lot of information that goes on. Let me show you this on a whiteboard, how this actually works. Let's take a look at our simple network. This time around, I'm going to use a little bit more than just 2 routers because I want to illustrate how GLBP works. So I'm going to use 4 routers that are providing some sort of gateway services to the inside of our network. Let me move this down a little bit here. Now, let's say that all these 4 routers are connected to the outside world. Let's say that this is our internet. So they are somehow connected here, and let's give them names. This is R1, R2, R3, and R4. And again, keep in mind that these could be our multi-layer switches. So these are not necessarily routers. These could be multi-layer switches. Now, configured here on this network, and let's say that this is in VLAN 10, so we are using 192.168, let's say 10.0/24, all of these routers have their own real IP addresses. So this is .1, .2, .3, and .4. Now, all of these routers also have their own physical MAC addresses. Based on this configuration here, let's say that we want all of our hosts that are connected to this segment here to use .254 as the gateway. So we want these 4 routers here somehow to agree and load share the traffic that all these clients are sending towards the internet and through the gateway of 254. The first thing that is going to happen when we configure GLBP, all of these routers are going to start sending the hello messages, and there they're going to have their AVG priority set. Now, based on this priority, one of these routers is going to be elected to be active virtual gateway. It doesn't matter which one, but let's say that our R2 here gets elected as an AVG. Now, AVG's role will be to respond to incoming ARP requests from clients. So let's say now that there is a client here that sends an ARP request. So this ARP request is a broadcast, so it will be, theoretically speaking, or not theoretically, but it will be received by all of our routers here. But all of these routers are going to be ignoring this request, and this is the ARP request for this address for 254. So this router here will ignore it, this router here will ignore it, and this router here will ignore this request. But R2, because it's configured as an AVG, will respond to this request and tell the client to use one of the virtual MAC addresses. The virtual MAC address will be the virtual MAC address that is associated with this IP address on R1, R2, R3, or R4. And let's say that R2 responds with the virtual MAC address of router number 1. So this client here, and let's call this client client number 1, will send the traffic towards the internet through R1. Now, let's say that another client shows up on our network. Let's say that this is client 2. Client 2 is going to repeat the process. It's going to send the ARP request. So let's simplify this. It's going to send the ARP request, and R2 is going to respond back. But let's say that this time R2 responds back and says, use the virtual MAC address of, let's say, router 3. So if client 2 wants to send the traffic towards the internet, what client 2 will do, it will send the traffic through R3 out of the internet. Client 3 might be using R4, client 4 might be using R2, and so on and so on. So this is how GLBP is actually able to provide load balancing through this separation of the gateway role and the actual forwarder role. But this is not where the story ends. What I have explained now was just one of the possible load balancing mechanisms that can be used by GLBP. And this was the simplest one, the round robin. With round robin load balancing, what is going to happen is that we are simply, with each incoming ARP request, we are going to respond with a different virtual MAC address, so that we are going to be using all of our active virtual forwarders. But as you might have guessed, this does not necessarily lead to the most optimum use of the resources. There are two different alternative approaches to gateway load balancing that GLBP can utilize. They are the weighted one and the host dependent. With the weighted load balancing mechanism, what is going to be happening there is that the number of ARP requests that are going to be responded to with the AVF's virtual MAC address is going to be directly related to the weight claimed by that particular active virtual forwarder. So let's say that one of the active virtual forwarders is claiming weight of 200 and another one is claiming weight of 100. The one that claims weight of 200 is going to get twice as many clients as the one claiming 100. And this is going to perhaps lead to more optimum use of resources. Let's say that one claiming weight of 200 has let's say, higher bandwidth available to the outside world than the one claiming, say, 100. Host-dependent load balancing simply means that the clients are going to be serviced with sort of sticky virtual forwarders. What I mean by that is that we are always going to give to the same client the same active virtual forwarder's MAC address, regardless of what they would be getting otherwise if we were using round robin or the weighted load balancing mechanism. And the last thing that I want to mention before I switched into explaining how this is all configured is the virtual addressing that is going to be used by GLBP. Unlike HSRP and VRRP, where it's enough to encode the group number into the virtual MAC address, with the GLBP, we actually have to not only encode the group, because we can still have multiple GLBP groups available on our interface, but we also need to encode the actual AVF number there. So the format of the MAC address is a little bit more elaborate than in the case of HSRP and VRRP. What we have there is the MAC address that begins with 0007B4, and then the next 16 bits, and in my example marked here with XXXX, are going to be encoded group address. But not all 16 bits are going to be used. The first 6 bits are going to be zeros, and then the 10 bits are going to be the group number encoded. The remaining bits, and this gives us 1 byte, that means 8 bits, are going to be simply an AVF number. So let's take a look how we can configure GLBP. This is not necessarily a very simple configuration of GLBP, but I wanted to show you a couple of things. So let's go through this configuration example line by line. So in the first configuration line here, I'm simply specifying the virtual IP address that is going to be used by my GLBP configuration, similarly to HSRP or VRRP. In the second line of configuration, I'm configuring the priority, but keep in mind that this priority will be used for AVG, the Active Virtual Gateway election process. It has nothing to do with forwarding. Then I'm configuring an authentication configuration here, and I'm using MD5 with the specified key string of Cisco, but instead of using the key string directly here, I could use a more flexible keychain, which is also an option for VRRP and HSRP. The next thing, the line number 4, configures weighted load balancing, and this is going to operate just as I described. Multiple active virtual forwarders are going to get as many clients as the weight they are claiming, or proportional to each other's weights. Now, with the configuration line number 5 here, what I'm doing here is I'm saying that the base weight, the maximum weight that this device can claim is 150. The default maximum is 100. Now, why is it called maximum value? Because we can have associated tracking objects. In this case, in lines 6 and 7, I'm tracking 2 objects, this time 1 and 2. And if tracking object 1 goes down, I'm going to decrement the claimed weight by this number here, and in the if the tracking object number 2 goes down, I'm going to decrement it by 30. So this is the maximum value that I can claim. But if one of the tracking objects goes down, what's going to happen is I'm going to decrement my weight, which means that other active virtual forwarders, based on my weighted configured load balancing mechanism, might end up getting a little bit more traffic than this forwarder here. Now, this value here, lower 85, that's a very interesting one. This simply means that if my advertised weight goes below this number, do not consider me as a viable forwarder at all. That means that if my claimed weight goes below 85, send all subsequent traffic to someone else. I am no longer able to forward this traffic. And in this case, it might mean that these 2 interfaces here have gone down. Now, in this particular configuration, not necessarily, but still, I'm just using this as an example configuration. In the last line, line number 8, we are saying here, GLBP1 forwarder preempt delay minimum 0. What this command here does, and this is a little bit complicated, it simply says that in a case that I need to take over forwarding role from someone else who has lower weight, do not wait any time before I attempt to do this. By default, GLBP is going to wait for 30 seconds before a preemption of forwarding function actually happens. And 30 seconds could be a very, very long time. Here we are saying, if I am better than other forwarders and I need to preempt them, I need to take over from them for whatever reason, do that immediately. Do not wait for 1 second.